Welcome to class 22. We'll talk about time inhomogeneous Markov jump process today. When we say time inhomogeneous, time is important when we start. Suppose you want to see the sales figure. If you go at 10 am in the morning or maybe at 3 p.m. in the evening time, afternoon time, definitely you will see different crowds. The crowd will not be the same. So we'll mention the time also. I'll go back to time homogeneous Markov jump process and I will write the notation and we'll modify that now. It doesn't matter where it starts and where it ends. We never mentioned the time. The only thing was to go from one state to the other state. Suppose this is the present state, the time is not known, and this is the other state j. You write random time here. What is the probability that the process will go from I to j in t time? Forward differential equation we discuss all the time, backward differential equation as well. So we have forward differential equation. Similar to this, we have backward differential equation. So we discussed about this already. Backward also it will be quite similar. Remember? Maybe I will discuss a problem also. I'll send you the recording for that. Here, suppose you need to complete task 1 to 20. When you divide it, you divide this way. 1 unit you make here and 19 units you make here. And suppose that you know how to manage 1 unit at a time, 1 unit of some task. You know how to manage 1 unit at a time. So you can divide this way, 1 to 19, 19 to 20. Then you will say, this I know I can manage. How about this? I will say repeat the same procedure. You divide it this way, 18, 19, 1, 18. Then what will happen? You will be able to manage this 1 unit. Then this will still be there 1 to 18. If you ask me how to manage 1 to 18, I will follow the same way. This is what recursion is. But forward or backward, remember in forward differential equation, we always write d by dt p I j t. When we write this way, summation p I k and mu kj. So when we write this, remember when we say p, we talk about this I to k probability. This is large one and mu is instant one. Okay, in discrete setting it's 1 unit I have taken. So if you divide this way, this will be forward. Okay, this one differential equation. When you consider backward, in that case you have to divide this way. 1 to 20 you can divide this way. 1 to 2, 2 to 20. Okay, so this mu will come this side. So in place of kj you write mu, then p will come here. So you divide this way, 1 to 2, then 2 to 20. You can manage 1 unit. Then the second one, 2 to 20, again you divide into 2 parts, 2 to 3 and 3 to 20. 2 to 3 you will be able to manage, then 3 to 20. That way you will do 1 unit at a time till you complete 20 units in the backward case. In the forward case you divide this way. Now coming back to this one, we'll introduce the time as well. Instead of saying the duration is t, the time also we'll write. We'll write this way. Probability, normally we define this way, and when we differentiated also, if you remember, we differentiated around t0, right? We wrote this one, d upon dt t0. This was mu. The definition of mu was differentiation of this, the rate of change of this, how the probabilities change with respect to time. Around the 0 we have taken, because around whatever point you take, it doesn't matter, it's time homogeneous. And the definition also, if you see, we never mind taking n to n plus t. It doesn't matter, you write n to n plus t or 0 to t. So if you see the definition of Pijt, we took from 0 to t, because 0 to t will be equal to 1 to t plus 1. Whatever you write, it doesn't matter. This was there before, no notation for the starting time. Always we have started from 0 to t, the duration was t, you can write anything here, but we consider this one. Here we'll write Pijt, we write both here. So what is the probability that the process will change state from I to j starting from time s in time duration t minus s. Okay, that is what we say here. And if you take s0, if you put s0, then you will get this one. So you can write this as a special case when s is equal to 0, and in that case it will be Pij0t, which is equal to Pijt. So in time inhomogeneous case we write both, because now we think that time matters actually. So the 1 month time you get to do something, suppose you want to do something between 1st April to 1st May, that might not be same if you are supposed to do that between 1 November to 1 December. Particularly for Indians, we have productive time during winters. So I to j here with starting time and ending time, that is given. So we'll start with integrated form of Kolmogorov backward equations, integrated form. So for that we'll introduce new symbols here, those similar. So let me write here time. Time starts here, from here, that is suppose s, and we'll find the probability that the process will transit to j at time t, starting with I here. So the state here is I, and we want to find the probability that it will be in j at time t from s to t. Whatever I have written there, that we'll try to find using integral equation. Okay, so there are certain things we need to consider here. First of all, to go to j from I, the process has to leave I. So here we'll use one. If you see, I have written 3 parts here. The probability of remaining in state I from time s to s plus w. So let me write here s plus w. This is the first part. And then making a transition to state L at time s plus w. Once I will leave this state, okay, suppose I am giving a class now. I want to be somewhere at time t. I started at 6 p.m. I wanted to be at some state at 9 p.m. So I have to leave the class. That is the first thing I have to do. It's not that when I leave the class immediately I will go to state j. Maybe I have something intermediate. Okay, so I have to leave. And here comes time. How much time I will stay from here to here. This is called holding time. Suppose I am in I will hold in this state. This is called occupancy probability. I'll try to occupy the same state for some time, suppose W time, before making a transition to some other state. Here if you see, the probability of remaining in state I from time S to time S plus W. We wanted to do this one, S to T. Now T is different time, J is a different state. We are in I. So first of all, I have to leave I. So what is the time I will stay here? For that I will write an expression. This one, the expression is e power, the same formula, minus integration S to S plus W. In homogeneous we wrote only 0 to W, S was not important. Whatever you want, U variable will write here, so that you will compare. The same symbol I want to use. This was already there, it's not a new one. Can you tell me the formula, anyone in homogeneous? What is the exact formula we use? We don't write this one. Remember, this is the, yeah, in ith state, okay, in ith state, whatever time one will stay, this time, this is the occupancy probability. Before moving to another state, this is the occupancy probability, okay, in whatever state you say, suppose I. So this was e power minus 0 to T. I mean, if you, it was actually e power probability that T naught, remember the waiting time, or maybe whatever time you give T, T is greater than, we use symbol T, right? And what was that? E power
minus lambda I.
Yeah, lambda I T, okay. So you can say this is Ti waiting time in state I. That was e power minus lambda T, okay. Here I can write lambda I dt, and lambda I, it will be a function of another, we will write this one dt, lambda I T dt, suppose you write. Here this is a dummy variable, so you can write lambda I U du. So this is the notation, okay. So they are exactly the same. The only thing is, at whatever time we are making a transition, for that we have taken, we have given this one S to S plus W. W is the time, remember. So this is also there separately, but I don't want to bring everything here. Whatever is required, we will discuss that, okay. Now S to S plus W lambda I U du, this was the formula. Then there is one making a transition, okay. So going to some other state, this state is L here. What is the probability that it will stay this time? We'll write the symbol for that as well. So let me write individually here. This one is e power minus S to S plus W lambda I U du. Then the next one, the transition is mu I to L, okay, state I to state L. This is the notation, and we have to mention time also. Remember, previously we used to write only mu, but now we have to, or we wrote mu ij, okay, I to j, similarly I to L, but you have to write the time also. At what time? Time is S plus W here, so we'll write S plus W. At this time, the process is making a transition from state I to state L. We just wrote mu IL in homogeneous case. Once this is done, then the last one, S plus W to T. It's recursion. We'll repeat the same. We'll write P L to J S plus W to T, which is equivalent to the original one P, it was I J S T. This is the left hand side. Okay, so we started from I, this is here, and we wanted to go to J starting from time S in time duration T minus S, that is at time T. Okay, so we started from here. We wanted to do something for the duration T minus S, okay, S to T, and the states were I to J. Similar thing came here. So it's not over, it's not a complete formula. It's not that you put something in RHS and you get the value of X in the LHS. If you put the value here T, you will get X. Not that way. It's a recursion. It's a kind of this AI minus 1. So similar kind of things will happen. A5 will be 5A4. It's not done. You need to know A4, A3. So everything is recursion here. So whatever way we started, similar kind of a thing happened here. This one. Okay, similar thing, same thing, but with a change state now, L to J. So it's not a complete solution, but it will help. Okay, so let me write the final one here, and here also I can draw something. Suppose our task was this initially. Our task was this. Now task reduced to this. So this was the first term, this was the original one. I mean, this is the left hand side. This is the third term. We have two more terms or expressions, I can say. We have two more expressions. Okay, so this is the waiting time, holding time, and this is the transition. Okay, the transition. If you make a transition, then only this will arise. So let me write J here. Now this one is equal to this multiplied by this multiplied by this. But this is not final, something else is there. So I can write P I J S T is equal to, these three I will multiply anyway. If you write ABC, I will multiply, but something more is there. So what will happen is, suppose I am giving you a class, I have to leave the class, and when I leave the class, where I will go? I have so many options. Either I can take another class, or maybe I can go and start some work I am doing for somebody, or maybe I can go outside to see how it's raining, or maybe something else. So we have to see at this time how many states are there. Though we are talking about continuous time stochastic process, we are not talking about continuous state stochastic process. We are talking about continuous time but discrete states. Discrete states here. Continuous time, continuous state, that will not come in CT4, I mean CS2. That will come in CM2 only. So states are there. So if I make a transition after this much time, whatever time I will occupy this, it's not fixed 1 hour or 1.5 hours, nothing is fixed. I will occupy some time. It depends. Once I leave this, where I will go, it will depend. So the L is not a known here, L is not fixed here. So you have to explore all the states like L. So I can write a summation sign, summation, and let me write all these whatever I have, e power minus S2 S plus W lambda I U du. Then the next one is mu IL. Still it's not over. There is something else we have to write. mu il, I need to write s plus w, then p lj s plus w t. So these are the three terms I've written, and I explored all the possible states I might go when I make a transition to some other state. L could be j also, that's a separate thing. But here at s plus w, if I make a transition, if I leave the state, I have to leave to get this one. So if I leave, where I will go, that is important. So I have to explore all the states, available states here. So summation sign I need to write. After summation, I have to write one integration sign also, because what will happen is the time is not fixed. The time, it's not like 1 hour. After 1 hour I will not leave. Nothing is fixed here. But what comes first? The integration will come first or the summation will come first? That is what we need to decide. I have to write integration sign here. I have to integrate between 0 to t minus s. Let me write, I have space here. Zero to t minus s I have to write. This is the complete formula. So let me explain once again why time I am integrating this one here. This is my timeline. This is s here. This is t here. Suppose I am presently in state I have to leave the state. So we are dealing in continuous time. In continuous time stochastic process, I have all the options. Suppose I am giving a doubt class. So whenever doubts are over, I will leave. So it's not like 15 minutes or maybe 30 minutes. It could be anything like 25 minutes, 3 seconds. Okay. So the time is not fixed. Suppose I will leave here and I will go to some state. L we already denoted. Okay. L. Then again I have to plan how to go from L to J in available time. Suppose s plus w here. So the time w, okay, starting from s, this time is not fixed. It could be anything. So this can happen this way. This is one possibility. What is the other possibility? Other possibility is I'll give you a 5 minutes class. Then I will make a transition here to L. Then I will decide how to go to J. This is a possibility. So these are all possibilities. Then I have another possibility where I will give a very big class, suppose up to 1.5 hours, 2 hours. Then I will leave the state, change the state to L, and from then I will plan how to go from here to here. So many options are there. Remember, these are the OR cases, because ultimately I want to be here in this state. Suppose we have a get together at time t. Now I am giving a class. So that way what will happen? Ultimately I have to reach here. That is my plan. So these are all the possible ways. So how many such ways are possible? Infinite, because time is continuous here. So I have to add all these cases. This one, this path, this is one, this is one, this is one. I have to add all this, because time is continuous. It can happen at any time, and we have infinite options are possible. So to integrate, that's where integration time comes. And when I write here, suppose dw, this time w could be 0. Okay, it will start from 0, and maximum value of w should be t minus s. You check here, maximum value of w is t minus s, so that s will cancel and t. Okay, so here the time when the time will be 0, when w will be 0, immediately, if I immediately leave the class here only, then W will be 0. If I leave here, that means I will continue giving you the class here only immediately when whatever 9 p.m. will when it will be 9 p.m. immediately I will leave the class. I will say no, I have to go somewhere. So maybe that is in the other room. Immediately I will go. I will make a transition here only. So completely I will stay here. That will be my holding time. So this is a variable. The minimum is 0 and the maximum is 1. But in between there are so many infinite options. That's why I need to integrate. Now fix one time. Suppose that time is fixed, okay? And here I am making the transition really. And the time is S plus W. W could be anything. Now here there are so many states where I will go. Suppose I am giving you a class. How many options are there? I can leave at any time, that's fine. And when I leave, where I will go, that is also one variable. I can go when I make a transition after spending some time here, occupying this state, where I will go. Then also I have so many options, but these are discrete options. That's why I have to write a summation sign here. And we'll see in example, we'll open the summation sign. Suppose 3 possibilities are there. We'll write all 3 possibilities where you will have integration signs. Okay, we have one example here. So this is called backward. See the heading, integrated form of Kolmogorov backward equations. Okay. Forward, remember, will give importance to this side. See, I'll write the similar diagram. Suppose I should be there at 9 p.m. We have a get together. I need to go there at 9 p.m. So I have to reach there by 9 p.m. We say on time delivery. On time. On time when we say exact time. But I have to reach here before time. If I want to be sure at 9 p.m. I am here, I have to go before that time. Okay. E minus W here. So I have to reach there by suppose 8:55 and I will wait, because what I am supposed to do is exactly at 9 p.m. I should be there. Suppose I want to go somewhere, so I have to reach airport whatever time is given. They said the check-in time is 9 p.m. You have to reach by 9 p.m. So it's not that I will reach exactly at night. Maybe I will reach at 8:55 and I will wait for some time there. So how I will go here, that will follow again the recursion pattern. So initially it was I to j will transfer this way. It was from I to j. Now we'll make it a time s by time t. That's what we have to do. So this one, if you remember here, let me write this. If you compare that one, we have divided this way. Initially we had this one, this big one, I to j, and we made it L to j. Now we gave importance to the present time. Okay, whatever time is remaining, that is called residual time. Here current holding time, oh sorry, we say current holding time, that is the residual. Okay, no problem, that is the residual time. That's why I deleted that. This is current holding time. See, the difference is when I say holding time, suppose someone is waiting here and wants to know when I reached here, and I'm waiting obviously here, so that at 9 p.m. I will get an entry. So this is my current holding time. Okay, current holding time. Holding time, when I say I will keep this state, I will not leave the state. Suppose someone comes here, I am giving a class, he will wait to talk to me. How much more time I will give the class? That means if you analyze it further, that says it doesn't matter. Suppose this is the room and I am here, I am giving a class and someone is waiting outside. Definitely this guy will not ask someone since when I'm giving the class. It's not important to this guy. Okay, so immediately will ask, the class is not over, what he's doing, he's giving a class. Okay, that's fine, but yeah, I want to know how much time it will take so that he can complete the class and he will come out. Maybe I'm giving the class since 10 a.m. in the morning. He will not be interested this one. Even if he can make a question, that will be second question. Okay, he will leave in 15 minutes time, that's fine, but since when he is giving the class? Then this guy says, oh, that you don't worry about that, since morning 10 a.m. is giving the class, but you wait 15 minutes. So what is important to this guy? This guy is the residual holding time. Residual holding time means what is the residual time? What is the time remaining? That is residual here. Maybe I will leave at 8 p.m. So 10 to 8 p.m. This is the total holding time. Even we are not worrying about the past. Maybe I am in this state before a long time, but what we are not discussing here is this one. The total holding time, if you calculate, if I leave here, if I make a transition from I to L here, so this will be the total holding time. This is the residual holding time. Because in Markov sense, past we never see, we are not worried about the past. But as I already mentioned you, we'll go to non-Markovian also when it comes to particularly the sickness. Okay, suppose I'll go to a doctor and I'm not well, definitely will ask me since how many days I'm unwell. If I suppose typhoid, what will happen is, if I'm unwell since last 20 days and I've taken already 3-4 antibiotic courses, maybe one more antibiotic course will work. I'll be well in another 5 days. But if I have typhoid and I'm suffering since last 2 or 3 days or maybe a week, it might take a lot of time. So the past is important. Even when it comes to exam preparation, you started a month before or 2 months before appearing the exam, that is important. So the time matters, history matters. It's not that it's independent of history all the time. So we'll bring this one then. Okay, since when I'm giving the class. Okay, my past is not important. What is important is, if someone calls me and says, let me know what you are doing, I will say I'm doing some work. Okay, maybe this is my work now, whatever I'm doing, I'm giving a class. Then he's saying, I want you to be here at this time. I want to be here at this time. So he's interested me to go there at this time, to this state. Okay, so this is not important now. This is important when I will leave this. And what is important? If I leave this, where I will go. These two things are important. So that's, in that sense, this is residual holding time. Okay, residual holding time. And when I say current holding time, because what will happen is, by the name, if this guy says, okay, that's fine, you are already here, I'm happy to see you here at this time. When you came here, that means this state and this state, they're the same. This is J. Okay, why we say current holding time? We say current holding time because he wants to know since when I'm here in this state. That means he is interested to know this time. This is called current holding time. Why? Both are holding times. Because I will not make a transition from J state here. I want to be in J, but I am before time. So I will continue in J after this also. But this is not important now. We don't want to see this one happening, because in our probability we are interested here, P, I, J, S, T only. What will happen, how much time we need to spend, that is not important now. So we are not interested here. Also, when you talk about current holding time, I'll not make a transition. I already made a transition, I came to J and I'm here, I'll continue in J. I'm not leaving this state. Okay. Residual word means what? How much time remaining? that is residual. That's why here we say residual holding time, because I will make a transition to some other state after this time. Okay, so if the total time is this in a particular state, here I am interested only this one, because I am starting from here. So after that I will make a transition. In the other case, I am not interested here, I am not interested here. This is J. Already I came to J here. Up to this I L. Suppose from some other time I came to J, I will continue here only after this. See, I will continue in J. Here continuation was in I will make a transition. That's why the name is residual. Residual means the remaining. What is the remaining time? That means I have to make a transition. That's where the name is changed, but the concept is same. And we'll write the three expressions here one by one. The probability that from I to K it will happen, then from K to J, and then from J to state J. Here P I J S T summation K is not equal to J, 0 to T minus S, P I K see the time also have to write here. This is the time, okay, T minus W. There we wrote S plus W because this was our subject. When a transition will happen, but here the transition will happen to J state, not leaving I. Here leaving I, here coming to J. They are different. So T minus W the same, but here we write the state from K, we came here. Suppose this was K state. So at this time, okay, we came to J. This is J. Already we are in J. All are in J. So mu Kj T minus W. Then this is forward, remember. We'll write the expression directly, minus T minus W to T now. Lambda I U du same. So this is one forward and this is backward. This is backward. Now along with this, we'll also write, suppose here in this case, P I I S T. Remember I is not equal to J here. If J is equal to I, let me mention here, if J is not equal to I, then this one. If J is equal to I, then there are two chances, okay. Either you will not leave I, because this I means what? Now I am in I, after some time I should be in I. This is the question. So here two things might happen. Either I will not change the state at all. Here we are talking about changing state in this time. Here what is the probability that I will be at I? So I am at I now. I will be at I. So this covers two things. One is this and the other one is, if at all I will change, I have to come back to this. So you change all J's into I's, you will get one expression. Plus another term you need to write. If I will change, if J is not equal to I, then you will get this one. Because I means what? You change, then come, then directly stay there. Okay, if you change to other state, you make a transition, then it will be exactly like this one. And if you will not make a transition, there you have to write Pi bar St. Similarly formula for I bar also. So if they are equal, then I will write here staying in the same state, Pi St. This is one, plus here we'll write the other part that will be the same. I just have to repeat whatever I've written. K is not equal to J, then 0 to T minus S, P I K S T minus W, then mu Kj, whatever, T minus W, then this expression e power minus T minus W to T lambda u du. So if you see this one and this one, this expression and this expression, so if J is a state, you are changing to K is not equal to J, and then 0 to T, whatever we have written, everything we have to write. So this will give one thing where I will be from I to I. And also you have to change one more thing, wherever J comes, there you need to write I, okay, wherever J comes, because there is no state J here. There is no state J here, okay. So you have to write that. So wherever you have J, you have to change that where J comes, okay, here only. So you write K is not equal to I, okay, K should be different, otherwise that will be included here. That's not a transition, okay. When we say this one, this is not a transition. Transition means what? I have to change the state. That's why we wrote this one here, and we'll write this one here as well. So K to J, but we want I to K, K to I, that's all. So what you will do is, all J's you replace by I, that one you will get here, and the other part Pii bar St you have to write extra. This is what I am saying. If they're equal, then you have to write one extra term. Otherwise, whatever is I, you write I here, and whatever is J, you write I here. That's what comes here. So these are the main expressions when it comes to inhomogeneous case. We'll visit one example. See, this is the example I gave you a week before. A three-state time homogeneous Markov jump process is determined by the following matrix of transition rates. The distribution at time 0 is given 1 by 3, 1 by 1, 1 by 3. Determine the distribution at time 1. When you see this kind of a question, though this is a repetition, remember the first thing you need to see is whether this is a continuous time stochastic process or this is a discrete time stochastic process. So when you see the transition rates here, and when you add everything, that will be 0. Make it sure these are mu ij's. So this is generator matrix, and from generator matrix you need to find transition matrix. So what we are doing here is, we are considering a continuous process which we want to analyze discretely. Discretely means what? Determine the time distribution at 1. 1 means maybe we want to see after each month, the change after each month, though it's continuous process, it happens continuously. I've given you an example. Suppose you want to see the stock price, it's a continuous process, it changes this way, but we are not interested in the continuous change. We are interested in discrete change. We want to know only at 1, then at 2, then at 3. That way, here in this question, they want to know what will happen at 1. So I need the probabilities. It acts like a discrete process, but the transition matrix is not given. So you have to find Pij's from mu ij's. These are the small Pij's from chapter 1. Okay, P21, P22, P23, P31, P32, P33. So from mu ij's given here, mu11, mu12, mu13, and these things you can estimate using sample 21, 22, 23, mu31, mu32, mu33. You have to get Pij, small Pij's from mu ij's. So these are the transition matrix probabilities, and these probabilities if you want to find, then there is one and only one way, Kolmogorov equations. Okay, they will come to rescue. There are 4. to differential equation, to integral equation, to integral equation. Though we studied integral equations today, both forward and backward, in non-homogeneous case, but we can use in homogeneous case also. This is a homogeneous case, okay? And we studied differential equations, the forward differential equation, backward differential equation, forward backward differential equations we studied in homogeneous case, but these are also fine in non-homogeneous case. We studied only for homogeneous. The same things we can write here also as well, and we studied these in non-homogeneous setting, but these are also applicable in homogeneous. This is a homogeneous case, okay? And I'll take you through the solution, because we want to find all the all the 9, but we'll not find all the 9. We'll find some, and there are relations P11, P12 plus P13, that is equal to 1. So if you know these two, then you know the third one. We need not apply Kolmogorov's forward equation. Okay, if you want to ask me which one is the best one out of 4, normally we try to make using differential equation, that is forward differential equation. But given a problem, you never know which one will be easier. You will come across problems where this kind of a one, the integral equation will be much easier as compared to the differential equation. So there are 4 ways. It depends. In some cases, this one will be easier. In some cases, this one will be easier. In exam setting, mostly if you see the questions, they will guide you towards a particular way of doing. It's not that randomly you have to pursue. It might be a difficult task, but yeah, you will be guided in the exam setting towards a particular equation. So there won't be any problem. However, by trial and error also you can see, and you can find it out what is the best one you can use. Okay, but ultimately you need to find all the probabilities P11, P12, P13, P21, P22, P23 and P31, P32, P33. There are relations, you can use those relations and you can decrease your time. This is the solution. Okay, so these are the 3 states here. Also, if you remember, we solved one question that is linked with CT5, where we had a diagram like this. We had a diagram like this, 2 and the third one. You can say active, sickness and dead model. Okay, so this is there, and you can make this and this way as well. Okay, so if you see this one also quite similar. This is kind of a dead state, you can say, but there is no return to 1. You can say this is a terminally sick, someone is active, or sick, you can say from sick one can die, from sick one can become terminally sick. So from terminally sick one can only die, that is state 3. Okay, there is no coming back to sick state that way. This is the diagram. So it's like a circular diagram. Okay, why I am saying this, there is a reason, because when you solve equations, you will be able to know when you solve a lot of problems, and seeing the question immediately you will be able to know what to do. Now this is what you want, but anyway you need to find those probabilities. It says P31 is 0. By the diagram you can see the probability from 3 to 1 is not there, 3 to 2 is not there, 3 to 3 is 100%. Okay, because that is a dead state kind of a thing. P2 to 1 is also 0, because there is no way you can go to a normal state, sick state, normal sick, you can say, from terminally sick, that is 0. So 1, 2, 3, 4 already we got. Then come to the diagonal entries P22. Because P22 is P22 bar here, if you leave 2, you can never come back to 2. See, inward entry is not here. Once you leave 2, there is no way you can come back to 2. That's why, see, once you leave 2, you go to 3. You are trapped in 3. You cannot go from 3 to anywhere. Forget about coming to 2. So there is no way you can come back to 2. Even there is no way you can come back to 1 once you leave 1. So what is the chance that I will continue to stay in state 1? The only way is continuously staying here, because if I leave I can come back to this. That's not possible in all the states. So we'll use the direct equations, direct formulas, and we'll find the diagonal elements here, diagonal entries here. So P22 will be 22 bar. For 22 bar there is a formula. For 11 also 11 bar there is a formula. Okay. So P23 also you know, because you know P22, P21. So you can know P23 also. Now P12 is not known. You have to find this one. And for this, what is used here? Integral form of Kolmogorov's equation. So when I send this solution, that time I remember I didn't teach. Today we discussed that. So how to use Kolmogorov's integral equation here. This was the solution. P12t, you can write 0 to t. Here s is 0 because we are talking about the homogeneous one. And see the exact formula, making a transition from 1 to t. What is left here? The time of making the transition, the time is t. T is not mentioned here. Though in our expression it was t plus w. Okay, it was s plus w. S is 0 anyway, but even we don't need the time of making a transition. So there is no time mentioned here, only mu ij, because we are in the homogeneous case. This is the transition one, and this is similar way, whatever way here we are talking about 1 to 2, that way we are talking about 2 to 2, t minus w. So P11 w, this is the first expression, P11 bar w, that is the holding time, staying in this state. If you see the difference, okay, if you want to compare with that one, P11 bar, I will show you here. Okay, if you say me, I'll write this expression. Okay, II bar. This one, this expression, we can change it to this one particularly. Okay, if you want, you can write for this one P. I'm in the state I, right? I bar. See, this is what appearing here. P11 bar W. So you write here P11 bar, staying continuously here. But there two things are not important, but here when we write in the non-homogeneous case, see, we write always 2 2. Okay, so here L to J, they are different, they are same here, continuously staying here. Okay, that we write, and 2 times you have to write. Okay, the starting time and the ending time. So we started at S and ending at W. Okay, S plus W it was. So S to T we have written the total time, here S to W you have to write. So this is equal to the expression. Okay, now coming to this one here, this one we don't have any time mentioned here, P11W, because W is the waiting time. Making a transition time is not required. So here if you ask me, this W is 0 to W. Okay, S is 0 here. Here the time is S2, here you see S to S plus W, and in homogeneous case we write 0 to W. Okay, even we don't mention 0, we write only W, S to S plus W. So both are important here. Now here P11 bar W, and then mu12, no timing is required, and this is P22 T minus W. Remember, we are not mentioning the time when we reach there. It's the total duration we write here. Okay, so these three are there. P11 bar P22 T minus W and then mu1 W, then write everything, and this is already there, e power minus 3W, and this is given already in the generator matrix P mu1 to mu1 to, and P22 T minus W, this is the formula by formula. Okay, so you just need to integrate this one. So what will happen is from non-homogeneous you can bring it to homogeneous and you can make it. We got it, and finally P13, we know P1112, so we know P13 problem is over. Then finally if you see, these are all the probabilities. So what happened is now it's exactly equal to the discrete case, because we have all the probabilities. This is our transition matrix and this is the initial distribution after one time period. What will happen? So you have to make the cross multiplication, matrix multiplication. This is a row matrix, this is the matrix, so you do that and you get the solution. So this was over. Now what we will do is we will try to apply Kolmogorov's forward equation to do this, and we will match whether we will get the same thing or not. Okay, so what we will do is, we got it anyway using the integral equation. We will use forward differential equation and we will see which one will be easier. This is one line or two line, that will also be one line in this problem, but you see in some problems they will not be the same. Okay, so let's do P1 to T. P1 to T will find here. Remember, this is the state diagram. 1 2 3, it was like this. So P1 to T, you have to find this one. Okay, and this one also, whenever we require, we'll bring from there. Even the question is here, I suppose. Okay, yeah, minus 3 2 1, minus 3 2 1, 0 minus 2 2, 0 0 0. These are mu ij's given, and these always we can estimate. We can't estimate these Pij's in continuous time setting. That's why we are studying Kolmogorov's forward and backward differential equations and integral equations. These are Pij's. You have to find mu ij's. These you can find from the sample, or you can make a survey also. Now we want to find this one P1 to T. Okay, if you know P1 to T, then you put T1, you will get this one also. Whatever it is, we need to know P1 to T. So to know P1 to T, either we can use directly or we will use the forward differential equation. That was, tell me how to make 1 to 2 here, because you can't go this way. There is no path this way, 1 to 3, 3 to 2. So we will not worry. So directly we have 1 to 2. So I think we'll have one term only. Sorry, we'll have two terms. Okay, so we'll write this way. Forward means P1 1 T mu 1 1. Okay, sorry, mu 1 2. Ultimately it should be 1 to 2, plus the second one is P1 to 2 you can write, and mu 2 2. Okay, so here mu 2 2 is minus 2. Okay, that's there, and mu 1 2, this is 1 2, mu 1 2 is 2. Okay, if I'm not wrong, this is P11 T. We have solved already these kind of problems. Mu 2 2 is minus 2 P1 2 T. Okay, now the problem is we need to get this one, and this one is here. This is the term which we don't want, but fortunately, because if you apply this formula, P11 T plus P12 T plus P13 T is equal to 1, like I mentioned in the last class. If you want to change this one by using this equation, and you have to, in some form, suppose instead of P11, I will change it to this way. If you go back to 2, then also you can come back to 1. Then what will happen, if I change this diagram to this way, like normal healthy sickness and death model, then you can find P11 directly. You have to apply this formula. When you apply this formula and you use forward differential equation, then when you replace this one by P12, this one, then along with P12, P13 will also come. So again, you will not be able to solve this. So maybe you will try some other way. You can try integral equation, or you have to try some other equations. That's not straightforward. However, in this example, we have already P11 bar. We have already P11 T, that is equal to P11 bar T. And for P11 bar T, there is a direct formula. Okay. Why they are equal? They are equal because there is no other way. Once we leave 1, there is no way we can come back to 1. So staying in 1 continuously or nothing is given, staying in 1, they are the same. That's why we can use this, they are equal, and the formula is there only for bar, and we already found this one here. This one P11 bar is e power minus 3t. Okay, we have this one e power minus 3t. So let me write it here. Now this becomes very easy. This is a simple differential equation dy upon dt, where I have taken y is equal to P12t. Then that minus 2 will come to this side. This will be 2y, where y is P12t. That will be equal to 2 e power minus 3t. Okay. So dy upon dt plus py, that will be equal to q. You are supposed to solve this differential equation. And it's quite easy now. There is no problem absolutely. Remember, here p and q's are either constants or functions of t alone. Here this is a constant, this is a function of t. If you remember, we solved a similar equation in the last class. Okay, so there is no problem doing this one. The model is this, knowing how we apply. Okay, because one more step of complication is added here. That's why I wanted to write this expression, so that you will have no problem when it comes to the normal integral equations. I don't know. Anyway, so the expression is like this. At time t, this is m. So the extra level of complexity, I can say, that I want to show you. What is the extra level of complexity they added here? Sometimes which makes life horrible. This one is here. Okay, this is what I want to explain you. And the summation will not write here. We'll write only integration, because we know the states, we can see whatever possible. Okay, so we'll write all this, whatever number of terms possible. 3 terms are possible here. I will write all the terms. That's all. 3 terms are possible here. Instead of writing the summation sign, we'll write 3 terms. Okay. Like suppose if I write p b to b, see this is where we will start, given. Okay, given that xs is equal to b, someone is bachelor or never married, you can say, and we'll write s2 t minus v. This alpha is like mu here at time t minus v. Remember what I am using. Then I have to write dv here. Then p b to w, this is possible. P b to d. We can check all these things. I am just copying whatever is here. Like these are monotonous, okay, the same expressions, but yeah, what is the change? That change I want to say you. Okay, so here if you see t minus v to T, all transitions I have to write du dv I should write a bracket here. I think maybe I'm unable to see there, because this will come, the two terms are here, two terms are here, two terms are, I mean two expressions are here, the third expression will be common. Remember what will come here, I don't have space to write, three things will come, okay? So that lambda I've written that time, if you remember, mu nu d will come here, because when you talk about this one, okay, let's not worry about this now, we'll go to that later. So these are the three terms, they're similar, okay? These two, and the third one is common, okay? These two, this is for the transition intensity, and these are, you can say, the corresponding waiting times, and we'll set limit also. The extra complexity, that level I want to discuss. This was not there before. Remember, we did this way, probability that xt will be equal to j when xs is equal to I. This was I j st, okay? This you can write this way, and this is exactly, you can see here, if you see given, what is given and what you are finding. The extra thing they've given is ct greater than w, okay? This was not there here. ct greater than w, this was not here. What is the meaning of ct greater than w? Okay, not explained here. Okay, ct is the notation we use for current holding time, okay? That means, suppose there is a guy now in 2021, and consider 2023, this is July, okay? This is July, this is July. So there is someone who is never married, okay? Suppose 20, 22, 25, whatever. His relative comes and says, see, I will visit you after 2 years. I will visit you after 2 years and make it sure that you will be in the married state. Also, you will be married at least for 2 months when I see. Okay, so exactly I will come after 2 years, and I want to see you married, and not only married on the same day, it should be at least 2 months. That condition is given. So that condition is here. So they've given the W we used, that W was different. They've given a W, they're saying the current holding time, okay? It's not the residual time, because he married here means he married already and he will continue to stay in this state, okay? So this is the current holding time, that must be at least W, okay? The current holding time must be at least W. That means suppose 2 months, 2 by 12. So I want to see you married. Not only that, so you need to change your status from B to M. Not only that, there must be at least 2 months, okay? So when I meet you, if you say no, I got married in 2020 July, that will be fine, because that is at least 2 months. 1 year before, that's fine. 1 month before is not fine. This is what they've given. The extra condition is this one. This one you have to use. So if you go by the diagram, in the diagram we talked about this. S here, time t here, t minus w here, okay? But there is another t minus w, at least. So at least means suppose this interval they are saying 2 by 12. It's not that, I mean, when he says I want to see you married for at least 2 months, that means it's not that he has to, I mean, go to M here only. It could be possible before also. So the W will bring here. Okay. So our W will change to a different, suppose it's V. Remember, V must be, I mean, this interval must be greater than this interval. Okay. So because this is our requirement, we'll try to complete the requirement before, here only. They can overlap also. The one of value of B is equal to W. In that case, they will match. This time and this time will match. So that way you form an equation, this to this, and then this one. So to make it sure that this one is satisfied, you have to change the equation a bit. If you go back to our file, here we have started from 0 to t minus s, but this will change to W, because minimum W, see, when we talk about where I have written D, it's not written the integral sign I have not written here I have written, okay, dW. Here what is the symbol, where is the diagram? Yeah, T we used, right? T minus W to T. So when you write this here, what is, I mean, how many expressions are here? 1, 2, 3. And when you write, this is from 0 to T minus S, okay? We talk about this one. If T is 0, that means you reach exactly at 9 p.m. So what is the maximum value of W? That is T minus S. In that case, what will happen? If you put T minus S, T minus S, then what will happen? That will be S only here. So immediately I will leave the class and I will go to that state. Suppose now 6 p.m. I will start. Immediately I will make a transition to the state I have to go. I will wait 3 hours and I will be here. So this is my current holding time. Okay, that is the maximum, because I'm here. At best I can make a transition now. I can go to past. That's what here. So 0 to T minus S. Okay, these are the limits. But now the minimum time here, that will not be 0, because when we say this is 0, W is 0, that means 6 to 9 I will give the class to you, and at 9 immediately I will make a transition, so that this will be 0. I will not go and wait. I don't want any waiting time. Okay, I don't want to make it sure that it should happen. I will not be 1 minute late so that I can go and wait before. I will not think that way. In that case, I will make a transition here. But in this case, what will happen? This 0 will become W here. That is the only change. Okay, and these things you can always see the expression. You can write all that thing. That's not a problem. The limit, you see, in the limit we have to start with W. This V we have introduced here, where I have written here V is at least W. Okay, you can't go, you can't I mean, make it 1 month. If it is 2 months, it could be 1 year. Okay, but this V will start from W. That's what you have to change. So W to whatever S minus T or T minus S you want, you have to write here. That's all. Every other thing is same. If you compare, we are using forward here. All other things are the same. There is no change here. Okay, the only change will come here for this condition, and this is one of the examples, the only one example given in your material, though it never came, I think, but yeah, that's given. When you go through the material, then you will not find it something new. That's why I explained you. This much only we'll discuss in continuous time, homogeneous, non-homogeneous. Okay, this much for today. I want to leave now. Thank you.
Thank you, sir.
Okay, fine.